All right. Give us just a moment here, please. The show will begin in just a moment.
All right. All right, Toby, we're live.
Hello, hello. Welcome to Æther Cosmology Æther Roundtable number 34. Today we are going to be talking a little bit about the old QED, quantum electrodynamics. Today Alan's going to be talking about it again. He's going to talk to us a little bit about the mysterious case of quantum electrodynamics and who done it, or actually who solved it. And so, yeah, thanks, Alan. We're looking forward to this one. I'm going to go ahead and kick it over to you whenever you are ready, sir.
Thank you, Toby. Much appreciated. So, yeah, like Toby was saying, we're going to be going over the case of who done it, right? Because all this mathematics requires a certain physical interpretation associated with it. So the physical correctness of reality depends on these equations and the interpretation of the mechanisms that ensue, right? That are described by the mathematics. So we're going to look at the history of quantum field theory, which leads to quantum electrodynamics, which branches off into quantum chromodynamics and the electron weak field theory or whatever. So we'll be getting into all of those. And what we're going to do is, to start us off, this is like going to be a lot of new terminology, new concepts and stuff like that. So I found a video that goes through it all really well and has excellent visualizations. It's 15 minutes long. So I'm going to play substitute teacher here and turn it over to my boy and let him walk us through an introduction to the concepts that we're going to be talking about, because it's the mechanisms that ensue as a consequence of these equations. So without further ado, let's get into it. So let me know if you guys hear the audio okay.
Yep.
Is that a perfect? All right, cool. So we'll let this play out and I'll be back in 15. Everyone be good.
Welcome back to Science Click. Today, quantum electrodynamics. When two electrons get close, they repel each other. This explains why we don't fall through a chair when we sit down, why we can exert a force on an object, and why the air exerts friction on a feather. Apart from gravity and radioactivity at the nuclear scale, almost all phenomena in the universe can be explained by how electrons behave. At first, one would be tempted to describe this repulsion by a force, the electromagnetic force. But electrons are not small marbles that would obey classical mechanics. They are quantum objects, particles, and to describe their interactions, it is necessary to reconcile electromagnetism with quantum physics. To this end, in the middle of the 20th century, the most precise model ever created in the history of physics was developed. An elegant model, simple diagrams to calculate with astounding precision the most fundamental phenomena of physics: quantum electrodynamics. Quantum electrodynamics is an example of a quantum field theory. We consider our universe as a sort of box, space-time, which contains two fields, fluids made up of mathematical objects: the electron field and the electromagnetic field. Within these fields move about small packets of energy that can appear or disappear, called particles. Electrons, for example, are disturbances that propagate like waves inside the electron field. The electromagnetic field also contains disturbances, quanta of energy, which can appear or disappear, photons. The field of electrons and that of photons are of a different nature. The mathematical objects from which they are made up are not of the same type. The electron field in particular is made up of spinors. rather abstract objects that are described by complex numbers. To simplify, we can imagine a complex number as having a size as well as a colour, its phase. When an electron propagates in the field, the phase of complex numbers rotates over time. This is called the electric charge. Electrons have an electric charge, which transcribes the fact that their phase turns as they move towards the future. Apart from electrons, this same field can also contain disturbances whose phases turn in the other direction. In a way, we could say that this is an electron, but which is moving in the opposite direction, towards the past. From our point of view, the phase of this particle seems to turn in the opposite direction. We perceive an opposite electric charge. This is called an anti-electron, a positron. On the other hand, the photon field is formed of vectors, which are expressed with real numbers. They are just ordinary numbers which have no phase, so photons have no electric charge. To understand how electrons interact, imagine that we place two of them at the start of our quantum field. In order to schematically represent the content of the universe, it is convenient to use lines to symbolize the movement of particles. A line with an arrow towards the future to symbolize an electron, with an arrow towards the past in the other direction to symbolize a positron, and a wavy line to symbolize a photon. To describe how particles evolve, quantum electrodynamics allows our two fields to interact using interaction vertices. An interaction vertex involves a photon and two particles of the electron type. These can be electrons or positrons, depending on their orientation with respect to time. Such a vertex can symbolize an electron which emits a photon, an electron which absorbs a photon, a positron which emits a photon or absorbs a photon, or even an electron and a positron which annihilate into a photon, or a photon which converts into an electron-positron pair. All these interactions are allowed, provided that for each vertex, the overall momentum of the particles in space and time, before and after the interaction, remains the same. The electric charge must also be conserved. Each interaction necessarily has an arrow that enters and another that leaves the vertex. By allowing our two electrons to interact with these kinds of vertices, we can then imagine a whole variety of different scenarios. In the simplest scenario, the two electrons continue in a straight line. In another, more interesting scenario, the two electrons exchange a photon, which acts as a messenger carrying part of the momentum of the first electron to the second electron. It is important to note that particles behave like waves. They can be exchanged along one direction, even though they carry a momentum which is oriented differently. That way, in some scenarios, the exchange will bring the two electrons closer. And in other scenarios, the exchange will push them apart. We can then imagine more complex scenarios, which involve many points of interaction. Electrons can exchange several photons at different places and at different times. Sometimes, a photon converts into an electron-positron pair, which annihilates to form a photon again. We call this a loop. An electron can also emit and then reabsorb a photon. As long as the overall momentum and electric charge are preserved, all imaginable scenarios, an infinity of more or less complex possibilities, can occur. And if we stop the evolution of the field after a certain time to look at the outcome of each scenario, we sometimes find our two electrons, and sometimes more particles, with some having appeared between the initial and final instance. Each of these scenarios, which start from an initial situation and reach a final situation, is called a Feynman diagram. Feynman diagrams transcribe the different possible evolutions of our quantum fields from a given initial situation. Apart from the initial and final particles, which are real particles that can be detected, the particles that act as messengers within these diagrams are said to be virtual. These are particles that cannot be detected, and they can exhibit some rather strange properties. They only serve as intermediaries to describe how our two electrons interact at a distance. Mathematically, each scenario, each Feynman diagram, corresponds to a very rigorous equation, and virtual particles are only a way of interpreting intuitively certain parts of the equations. That said, although they are only intermediaries resulting from our mathematical model, it is essential to consider these virtual particles, because they account for the interactions of the fields, and therefore how electrons behave. Let's summarize what we have so far. We describe a space-time which contains two fields, that of electrons and that of photons. From an initial situation with two electrons, we are interested in all possible evolutions, allowing interactions that link a photon to two particles of the electron type. From this, we can create a catalogue, a list of all the possible diagrams. There are infinitely many. Some are simple, contain few interactions, and others are more complex, involving many interactions. But this doesn't help us too much. If we wish to predict the actual behavior of electrons, we'd like to know which of these scenarios actually occurs. If we carried out the experiment, is it this scenario or this other scenario that would occur? The answer to this question is subtle and may seem counterintuitive, but it is precisely what makes quantum theory so powerful. Our universe does not follow just one of these scenarios. It evolves at the same time according to all possible scenarios. In a way, starting from a given initial situation, all possibilities occur at the same time, in parallel, as a superposition of every imaginable scenario. To describe the behavior of electrons, it is necessary to take into account all Feynman diagrams. In quantum electrodynamics, each diagram corresponds to an equation, which allows us to calculate a number for each scenario, an amplitude. We can imagine the diagrams as layers, and their amplitude as a sort of opacity that sometimes adds up constructively, and other times destructively. The many different scenarios have different amplitudes, but for the sake of calculations, we can usually neglect the more complex scenarios, considering only the first few simplest diagrams, and still get reasonably accurate results. It is by performing the sum of all these scenarios with their different amplitudes, as if we superimposed more or less opaque layers, that we obtain the real evolution of the physical system. When we carry out the experiment in the real world, if we throw two electrons and observe them a little later, the amplitudes of each diagram allow us to calculate the overall probability that we observe a specific outcome as the output of our experiment. And in particular, the most likely outcome is that we observe our two electrons with slightly different momenta. They repelled each other. In a way, Feynman diagrams are not so much descriptions of real phenomena, but rather very powerful tools that allow us to calculate the probability of observing such or such an outcome. We have a greater chance of finding our two electrons with outward momenta. The most likely outcome is that they repelled each other, thanks to the exchange of virtual particles. At our scale, we have the impression that the two electrons undergo a continuous force, while fundamentally, this force is only the probabilistic synthesis of all possible interactions, in which the electrons exchange motion through virtual particles. To conclude, quantum electrodynamics is a complex theory, but it allows us to predict in an astounding way how electrons, positrons, and photons interact. By synthesizing all possible scenarios with their different amplitudes, this theory explains and predicts at the fundamental scale all the laws of optics, the behavior of light when it interacts with a material, Maxwell's equations, which govern electric and magnetic fields, and interactions between electrons, from which at our scale almost all forces arise. Historically, this model was the first great success of quantum field theory. By describing matter as quantum fields, interactions as virtual particles, and proposing a very elegant calculation method based on diagrams and amplitudes, quantum electrodynamics has in particular allowed scientists to predict with an unprecedented precision the way in which an electron reacts to a magnetic field. Through virtual photons, the magnetic field causes the spin of the electron to precess, and this precession motion is perfectly predicted by quantum electrodynamics to almost 10 significant figures. To this day, all theories considered, this is the best verified experimental prediction in the history of physics. The anomalous magnetic moment of the electron.
All right, fantastic. We got some nice visuals there. We got some nice concepts. So
I feel educated, just so you know.
yeah, what we learned there is that there's a field that gets interacted with, and there's magnetic moments that so that they're taking energy readings, right? And they're like, there's a predicted amount of energy that should come out of this, but there's a deviation from it. So how do we explain that? Well, they explain it by maybe there was an interaction with virtual particles and anti-particle pairs. Maybe they interacted, annihilated, and then that ejected a little bit more energy, stuff like that, right? So that's like the basis. That's like the base premise of what's going on there. So we're gonna get into it from there. I'm gonna see when I close this video. Okay, so here we are. They put together these great physics conferences, starting with the WWII conference, and then it was picked up by Oppenheimer.
Wait, what?
What's that?
What was it called?
You never heard of the Solvay concerts? Conferences?
Oh man, it's the WWII. Okay, all
Oh,
right.
did I say that? Mispronunciation. My bad. So yeah, the old Solvay conference. So anyway, the physics lads here get together and they decide how they're going to interpret reality. So if we recall back to the old previous frameworks of the ether being a fluid medium that permeates all of space, and all of motion would be relative to it. Well, when they tried to measure the motion of the Earth, they got rid of that theory, right? So there can't be an ether, but they have this field that they can interact with and make measurements with on the on a really small scale. So they need to quantize that and describe that without alerting everyone that the concept of an ether is real. So to go over the lads here, we got Schrödinger, we got Wolfgang Pauli, we got Heisenberger. We all remember him from Breaking Bad. And we got, got a couple other lads. We got Dirac, Compton, famous from the Compton scattering. Got D. Broglie, Niels Bohr, Max Born. Shout out to him. who found who didn't find the electron in the cloud of probability after squaring Schrodinger's wave equation. Got Max Planck, Lorentz, Einstein, Paul Lavoux, who came. This is the guy that came in to fix the Sagnac effect for Einstein there with general relativity. And I think that's about it. And then over here, a lot of people think that this is Adolf Hitler, but it's Joseph Peter William Debye. So that's who that is.
Did you catch Picard in the back left?
No, I totally forgot to cover Picard. Thank you.
That's the boy who went up in the balloon and saw that it was flat.
That's the old balloon lad, dude.
Looks
And
flat
then-
with upturned edges, he said famously.
Well, turns out there's an academic paper that says that can't be corroborated that he ever said that. So, but anyway, we can come back to that for funsies. Shout out
Comics
to
lore.
yeah, dude, it's all mythology, it turns out. But anyway, so the other characters are the electron here, which is the basis of subatomic particle interaction. This is how they're going to build everything off of this metric. Everything will be in relation to the electron. And to discuss how they came up with the electron there, we have J.J. Thomson in 1897 doing a cathode ray experiment. So he has a vacuum tube, a cathode, and an anode. And what they're doing is they're essentially putting electricity through this beam. They have a filament in here, so it lights up the beam so they can see a coherent green color. Then they have a scale on the other side of the tube. The energy beam it goes directly through the center there, and then they can introduce electric and magnetic fields here in the center.
Oh, did we lose Alan's audio?
Sure did.
Alan, I think your mic maybe cut out just now.
Yep. I can see his mouse moving.
Yeah.
Testing 1, 2.
Oh,
Oh, dude,
now we hear
OBS
you.
There
crashed.
you are.
OBS crashed. 1 second. Let me restart the live stream.
Oh, no.
This is probably Linux.
No, I'm on Windows. Nice try.
Yeah, it was probably Bill getting his little nose in there.
Yeah. Yeah, my bad. When did you guys lose audio? I heard it ping out, but I didn't realize it was OBS. So that was my mic.
That was only 10 seconds or so.
Ma-
20.
Magnetic field was the last thing you said.
Oh, cool. Not bad. Thank you. Okay, cool. So they got this beam going through here, and they introduce an electric and magnetic field to get a deviation from the center here, and they measure that. Now on the back end here, this anode and cathode, they know exactly how much energy they're introducing to the system to get that beam. So they're looking for the lowest amount of energy that they can input into this system, get a deviation from the electric and magnetic fields, and still get a quantifiable measurement, right? And then from that amount of energy, J.J. Thomson came up with a coefficient to distribute that around the surface of a sphere, which gave them and then from that, they had, their angular momentum and mass that they could attribute to it once it was a little tiny sphere. And then that's how they got the mass of the electron. And then obviously Einstein came along with E equals mc squared and gave a more precise number to that electron mass. But that's basically how they do it. So anytime they take an energy measurement, they can convert that into the mass of the object, right? So that they do the same thing with the muon. And they say that it's very similar to the electron and it has a very similar magnetic moment. And what the magnetic moment means is what we're going to be talking about here is the quantization of the electromagnetic field that Dirac was famous for with his equations. And they have an expected amount of how much these things should weigh and whatnot, right? In their uncharged state. So when they're charged, when they're moving through the field, they become charged. And in that moment, that's where they measure the intensity of the magnetic field of the energy that they're measuring. And based off of that, they're like, okay, that must mean we were right on our calculations, because if it weighed this much and it's accelerating through the field at this orbital velocity, at this orbital radius, right? They can reverse engineer all of that, all of the parameters of it based off of those fluctuations. And so the prediction of this magnetic moment, of the strength of that magnetic field that they measure, is very important to them, because off of the back of that, it quantifies the physicality of the Feynman diagrams, right? All the stuff that guy was talking about, where they have electrons that go back in time, positrons, all that stuff. all of that hinges on the strength of magnetic fields that are being measured at a specific time. Right. So, and then we have the muon G-2. So we've heard them talk about that, where they have the most precise measurement of that anomalous magnetic dipole moment. And again, they say it's an anomalous moment here because this is a crafty way of them turning the falsification of their model into the proof of it, right? So quantum field theory, Dirac's equations make a precise prediction about how the strength of that magnetic moment should be when they apply a charge to that uncharged particle. And there was a deviation from that in the measurements. And so they were like, oh, how do we explain that? Well, that's where they insert quantum electrodynamics, and they go, well, maybe there's a possibility of all these combinations that happened. And, that causes the fluctuation, right? And the correctness of that gets allegedly predicted out from the equations, right? So they say that they have a measurement of the magnetic moment down to 0.14 parts per million. So they have the most sensitive, accurate, precise measurement of the magnetic field, and that's all in alignment with these equations and these predictions. Well, how did they do it? That's what we're going to be covering, because of the techniques that they use to produce these and act like it's is a prediction of theirs is dubious to say the least, right? So to get into the start of it all, we're going to start off with Lamb shift before we get to the magnetic moments and stuff like that. The first deviation from quantum field theory from Dirac's equations was Lamb shift. Now, this was where they have the conceptualized model of how hydrogen should work, and it should have two electrons orbiting its nucleus, and the energy from that should be equal, right? Now, when they took spectroscopic measurements, they found that the energy, so they're looking at emission lines, and they found that their measurement was off from Dirac's prediction. So to do that, or to satisfy, to rectify like that difference or whatever, a guy named Hans Bethe comes forward and presents some recalculations, and we'll get into all that. But basically, they start to reintroduce like a physical mechanism of quantum electrodynamics to explain the deviation from quantum field theory. So they're saying that like there's an even smaller interaction that's happening on the subatomic level, right? So that's where we get into leptons and fermions and all these charged particles and all that stuff. This is like where they had to take it to facilitate that deviation from their prediction of quantizing the field, and quantizing the field means that they're turning it into discrete packets of energy rather than continuous lines of force. So if you've ever looked at a ferrocell and a magnet and you see those nice continuous lines, they're like, no, that's some sort of an illusion. What's actually happening is those are little tiny microparticles that pop in and out of existence through the interactions described by Feynman's diagrams, right? So I came across this paper. Shout out to Robert Bennett, who pointed this out. This is Oliver Kanza, who writes a paper called "Something is Wrong with the State of Quantum Electrodynamics." And he goes over the history of these equations and how they solve them, and how they solve them is where it gets into, that's what ruins the physical meaningfulness of these equations and the elegance of the Feynman diagram. And all this turns out to be built on a house of cards. So we'll read a little bit here from the paper. Quantum electrodynamics, QED, is considered the most accurate theory in the history of science. However, this precision is based on a single experimental value, the anomalous magnetic moment of the electron, the G factor. An examination of the history of QED reveals that this value was obtained in a very suspicious way. These suspicions include the case of Karplus and Kroll, who admitted to have lied in their presentation of the most relevant calculations in the history of QED. We will demonstrate in this paper that the Karplus and Kroll affair was not an isolated case, but one in a long series of errors, suspicious coincidences, mathematical inconsistencies, and renormalized infinities swept under the rug. So to start us off here, and I've kind of talked about it a couple times, but Dirac makes it very clear here what the issue is, because when you go to look into quantum electrodynamics and quantum field theory and all that, you're immediately hit with how elegant it is, how you can't understand it because it's too crazy and weird, and all this stuff, right? But this is pretty straightforward. So it says, the renormalizations we have in the present quantum electrodynamics comes from starting off with what people call a bare electron, an electron without a charge on it. but at a certain stage in the theory, one brings the charge and puts it on the electron, thereby making the electron interact with the electromagnetic field, which this brings in perturbation into the equations and causes a change in the mass of the electron, which is represented by delta M, which is to be added to the previous mass of the electron. This procedure is rather roundabout because it starts off with a rather unphysical concept of a bare electron, and probably the improved physical picture we shall have in the future, the bare electron will not exist at all. So what he's saying here is when they've got their nice little quantized field, and then when they apply a charge to the thing that they say has, intrinsic angular momentum and all that, when it pops into existence and interacts with the field, it's expected to have a specific amount of energy to give that magnetic moment. And there's a deviation from that. So that, this is how they have to explain it. So pretty straightforward. And then he goes on to talk about the renormalization, because this is going to be hugely significant, because these are the techniques that deal with infinities in the equations, and they use these to rein them in and make them, solvable to give this quote unquote prediction. But the prediction comes at the cost of accepting these crazy physical mechanisms that can't possibly be true. All right, so here we have the class 2 difficulties are really serious ones. They arise primarily from the fact that when we apply our quantum theory to the fields, we have to make them agree with special relativity, and it's the way that they have to do that that causes issues as well. So interpreting them in terms of three-dimensional sections, I have mentioned that we have equations that they at first look all right, but then when you try to solve them, they do not give solutions, meaning that they diverge into infinity. Then he says, one gets the integrals that diverge instead of converging to something definite. Physicists have found that there are ways to handle these according to certain rules, which make it possible to get definite results. This is known as the reformalization method. The renormalization theory has removed the class 2 difficulties if one can accept the illogical character of disregarding infinities. And he was heavily against this because it doesn't make sense to disregard them just because they're there and you don't like them. And it undermined the possibility that they were physically correct, right? Because essentially they're just making the math fit the observation at this point. So this is from his later in his career. These are his thoughts on it. So we're doing a little backtrack here to understand the thought process behind renormalization, because that's all quantum electrodynamics is. It's all based and facilitated by mathematical tomfoolery. Mathematical hocus pocus, to quote Richard Feynman. So let's see. I do not mean to get back to the pic. Okay, so in his later years, he goes back. He wants to go back to an ether theory here. So he says, I do not mean to go back to the picture of an ether one had in the 19th century, but I do mean to introduce a new picture of the ether that will conform to the present ideas of quantum theory. The objection of the old idea of the ether is that if you suppose to be a fluid filling up the whole of space, any place in it has a definite velocity, which destroys the four-dimensional symmetry required by Einstein's special principle of relativity. Einstein's special theory or special relativity killed the idea of an ether. But with our present quantum theory, we no longer have to attach a definite velocity to any given physical thing, being the cause of the velocity is subject to uncertainty relationships. So what he's saying here is through quantum tunneling, quantum entanglement, and superposition, they can get around not having to worry about measuring the relative velocity of the ether, which would reintroduce the problems with, why can't we measure the Earth through space? So he's like, hey man, maybe we can just have the ether and have it function in a special way that velocity is not relative to it. And, so anyway, that's what he's saying there. Is there's a lot of talk lately of like, oh, maybe we can just bring the ether back and ether Einstein, and nah, it's you would have to explain this velocity issue here. So it would, however, mean the departure from the notion of the vacuum that we have in the quantum theory, where we would have to start off in the vacuum having the state exactly the symmetry required by special relativity. So that right there, he's kind of saying it. So it wouldn't be the same as like the fluid medium propagating everywhere. because again, with Einstein's theory, that would completely destroy it. So, and he goes on to talk about continuous lines of force. So we'll talk about that. And it's like, and this is to show the contrast of the opinions of the founders of quantum electrodynamics before we get into the history of it. Why did they change their opinions? What was the issue with all these renormalizations? If it's all cool and above board and makes sense and it's logically coherent and mathematically consistent, why is this dude talking about going back to an ether theory? So now that the state of affairs is just what we have with discrete lines of force, we can picture the lines of force as strings, and then the electron in this picture is the end of the string. The string itself is the Coulomb force around the electron. The bare electron means the electron without a Coulomb force around it. It is inconceivable with this picture, just as it is inconceivable to think that the end of a piece of a string without thinking of the string itself. This is, I think, the kind of way we should try to do and develop our physical picture, to bring in ideas that make inconceivable the things that we do not want to have. Again, so what he's talking about is the issue with them making everything discrete quantized chunks versus continuous lines of force. Super logical. You can't even conceptualizing it is, he's saying it's low key R worded. Then he goes on to talk about a little conjecture for his new ether theory that probably never came about. So the muon has a surprising property of being almost identical to the electron, except in one particular, namely its mass is 200 times greater than the mass of an electron. Apart from this disparity, the mass of the muon is remarkably similar to the electron, having an extremely high degree of accuracy. The same spin of the magnetic moment is proportional to its mass of the same mass that the electron does. So again, they're measuring these things based off of what they would be uncharged versus when they interact with the field, and then the intensity of that magnetic moment, right? 1 second, getting some water. They're saying they're oddly similar, but definitely not the same thing, or whatever. So this leads to the suggestion that the muon should be looked at like the excited state of an electron. If the electron is a point picturing how it could be excited, becomes quite awkward. But if the electron is in a quite stable state in an object of finite size, the muon might be the excited state, which it undergoes of an oscillation. So what he's saying there is maybe it's like there's a little oscillatory action, and that's kind of the conceptualization of the interaction that I think that the ether has with, how it vibrates and oscillates. Everything's an oscillation and vibration. And then within that, there's different elevated states of oscillation. Like it's, the frequency is happening faster or in a more compact area, which gives a different structure to matter, or, it carries a different momentum to it, et cetera. And that's what these measurements are all about. It's not about little tiny billiard balls oscillating around or whatnot. And then, this diagram on the right here, which has the continuous lines of force that go to termination, is the electron and positron for how he was conceptualizing his new ether theory. So this is, makes sense. Everything, goes and terminates in on itself. Very cool. Okay, so for the renormalizations, there's a couple techniques that they use. They use substitution. So this is how to deal with infinities. So this is replacing a divergent series with a specific finite value of an arbitrarily chosen value. So this is them just, choosing what to solve essentially, right? And then they have another technique where they do the same. It's all the same, like pick and choose of how we're going to solve it, right? So another way that they can do it is separating the infinity into two components. One diverges at infinity and the other converges at a finite value. So what they do there is they'll separate the electromagnetic spectrum. Anything that oscillates at a certain high frequency, like the UV frequency, they go ahead and say, okay, those all diverge to infinity. So we're going to ignore that. And we'll just look at the lower end of the spectrum and we'll solve for those because those give the appearance right now of convergence. So that's good for us. So that's one way that they'll do it. And then another point is just to arbitrarily introduce a term that arbitrarily cuts off the series and just ignores you basically just ignore the divergence. Anything that's going to diverge, you just go ahead and automatically ignore it and continue to try and solve it out. And then anytime it pops up, you just interject your boy cutoff. So the renormalization techniques leads to quantum weirdness, right? This is the layman description of quantum weirdness. This is the, wave particle duality, where waves exhibit particle-like properties. This is the uncertainty principle, where you can't measure it, but it's definitely a particle. It's in a cloud of just probability. We get into the collapse wave function, where when you try to measure it, that's when it collapses, and you'll actually never know, because it's like Houdini. And so yeah, it just never ends with it, and then you end up with virtual particles, which is the emission and reception of photons that mediate the electromagnetic forces of the particle, right? So when they was talking about, it exchanges information that carries the momentum of it and all that, it's like, this is where all that stuff comes from. It's not an actual physical mechanism. It's just an abstract mathematical explanation. And then they teach you the Feynman diagrams to kind of give meaning to it, but they're physically meaningless. And that's why all these people were abandoning these theories at the end. So to kind of recap here, to get us back on track now that we've learned a little bit about renormalization and what the father of quantum electrodynamic field, or what the father of quantum field theory and quantum electrodynamics thought, we will continue on here. So remember, this is a battle for the physical correctness of the equations, right? It's cool that they get the predictions and they have the instrumentation to make the measurements and stuff, but is the story physically correct? All right. So to give a little intro into the paper here of how we got here, like how did we get to the obvious conclusion? I'm sorry, how did we get to the non-obvious conclusion that there's no continuous lines of force and everything's a quantized packet and all this, right? So at the end of the World War II, physicists organized a series of transcendent conferences for the development of modern physics. Shelter Island, 1947, Pocono, 1948, and Old Stone, 1949. These conferences were intended to be a continuation of the mythical Solvay conferences, but after World War II, the world had changed. The launch of the atomic bomb in Hiroshima and Nagasaki, followed the immediate surrender of Japan, made the Manhattan Project scientists true war heroes. Physicists were no longer a group of harmless intellectuals. They became the powerful holders of the atomic bomb's secrets. They were militarized, and their knowledge became state secrets. There was a positive aspect of this, and that was the atomic energy emission. Yeah, good job, government. Nice. See, the former members of the Manhattan Project took control of universities and research centers. They were given generous grants from the government. They were allowed to invest in expensive experimental resources, such as particle accelerators, supercomputers, or atomic explosions. But no one considered the risk to future science. The former members of the Manhattan Project now enjoyed unlimited credibility. Their hypotheses were automatically accepted, and no one could refute their theories. Their calculations and experimental data were subject to military secrecy, and at the cost of the equipment necessary to conduct the experiment was prohibitive for the rest of the international scientific community. Consequently, all the calculations and experiments could no longer be reproduced independently, and those who accepted their hypotheses were rewarded with good jobs and worked at research centers and universities, while the others who criticized their work were ostracized. So this is going to be a follow-up on how all these, because it's like, wouldn't the physicists have known? Are you telling me you're right and all these people are wrong? How did they not know? It's like, well, it was just forced down their throat, and the correctness of it was the only way that they could move forward without an ether, right? And still keep the motion of the earth around. So everything hinges on people getting paid not to have a vested interest in looking too hard into this. So some more from, let's see, I think this is from Dirac here. So he says he's strong. Yeah, this is from Dirac. So at the end of his life here, he's just talking about how the theory was complicated and ugly, and he's talking about the renormalization methods. And he says that it's just not sensible mathematics to neglect a small quantity is sensible because it's a small quantity. Not neglecting something that's infinite because it's large and you don't want to deal with it doesn't make sense. Like it's not the same thing. And then Dirac admitted, from an instrumentalist point of view, the renormalization that the renormalization techniques allowed quantum electrodynamics to be an undeniable success. but at the cost of, logical coherency and the physical meaningfulness, right? So he goes on to say that, but at the price one must pay for this success is the abandon of logical deduction and replace it by working rules. This is a very heavy price, and no physicist should be content to pay it. So again, we're talking about the big G's here that understand the math and what's going on, and they're diverging from the theory that they were putting forward. So that was from an autobiography from him. So it's eating him up that the math is meaningless, right? Because he worked really hard to put all this together. A lot of people did, actually. So this is from an interview from Paul Buckley let's see, where he says, would you comment on the divergences of the infinities that occur in quantum field theory? Many think that they have been removed by renormalization. What is your feeling on this? He says, this is just a stopgap procedure. There is some fundamental change in our ideas and probably, let me start that over. There must be some fundamental change in our ideas, and a change just as fundamental as the passage from Bohr's orbital theory of quantum mechanics. When you get to a number turning out to be infinite, which ought to be finite, you should admit that there is something wrong with your equations and not hope that you can get by just doctoring up the numbers. So he asks a follow-up question. Some people are introducing this curved space-time to get rid of these infinities. What do you think about that? And he's like, nah, it's still full DS. If you have a good theory, you shouldn't need to solve infinities or sweep them under a rug or curve space-time, which also leads to infinities and doesn't really help anything anyway, interviewer guy. I added that last part. Dirac didn't say that.
Are you sure you quoted dog shit? Because I believe you. Say so.
I mean, Dirac was the OG DSer, dog.
It's Dirac, and all you needed was the French accent. I would have been convinced.
Dirac? How do you say it again, Stone? Dirac? Dirac. All right. Dirac. Okay, so Richard Feynman says here, so this is the Feynman diagram, lad, right? So this is his thoughts on renormalization. So it appears the only thing that depend on the small distances between coupling points are the values for n and j, theoretical numbers that are not directly observable Anyway, everything else which can be observed seems not to be affected. The shell game that we play is to find n and j is technically called renormalization. But no matter how clever the word is, I would call it a dippy process. Having to resort to such hocus pocus has prevented us from proving that the theory of quantum electrodynamics is mathematically self-consistent. It is surprising that the theory still hasn't been proved self-consistent one way or another by now. I suspect that renormalization is not mathematically legitimate. Oh, no way, dude. So that's super unfortunate for the math lads, right? Because it turns out that none of these Feynman diagrams are solvable without renormalization, and all renormalization techniques are going to diverge into infinity anyway, it turns out. So that's super unfortunate for the physical meaningfulness of this. So this is, Feynman speaking on this, right? So let's see here. Towards the beginning of the prez, we were talking about the divergence from the classical theory to the quantum field, or from quantum field theory, where they got their measurements that led to quantum electrodynamics, right? So this is the Hans Bethe guy that I was talking about that came up with a solution to the Lamb shift, and he uses the value k here, which is a system that which is a series that diverges into infinity. But basically, what he did is he, did some renormalization, and through that was able to explain the deviation, and with that they got their foot in the door with quantum electrodynamics. And then after that, a guy named Schwinger came through with a more elegant formula that doesn't have a huge divergence built into it immediately, with G1 equals 1 plus alpha over 2 pi, and everyone was like, "Oh, that's super cool. I like that." And the only thing is, he never told anyone how he derived alpha, how he came up with that. And he says in his published paper that a paper dealing with the details of that theory is forthcoming, right? So turns out he never published that, and he gets invited to the Peccano conference in 1948 to explain it to the boys. So him and Feynman go to explain their theories, and this is one of the guys that's coming through to explain his situation and how he derived alpha for the solution for that. Now his presentation lasted 5 hours. It was just all, a string of mathematics that nobody could understand. And he had no physical mechanisms for anything, i.e. he just, did some fudge factor numerology stuff to introduce the value for alpha. The author of the paper, the Kanza guy, says that he suspects that the technique he used was called numerology, where you would assume that the G factor should be directly related to the fine structure constant, which gives the approximate value of 0.7. If you divide that by 6, it gives an approximate value of 0.1, which is the experimental deviation measured by Rabi. So he just saw the relationship there and then interjected it and then tried to build a mythology around, how he did that, and nobody was buying it. So it was a pretty big disaster there. There's some negative. He got a lot of negative feedback on his Yelp review for that one. And then Feynman came through with his Feynman diagrams, and which was the same thing. So he had this equation to give the solution, but he had no explanation of how he derived it as a consequence of, Dirac's equations or anything like that, right? Of the quantization of the field itself, right? Because it's extremely important to show how your theory is derived, where it came from. It's building upon. Your theory is building on Dirac's equations. How did you derive your diagrams, Feynman? Is it related to? No. Oh, you can't tell us, but you don't care because it just gives the correct solution. And that's where he gives his famous quote about "shut up and calculate." Right? Everyone was like, "Yo, Dirac, how'd you do it, broski? What's your physical mechanism?" Actually, he had the physical mechanism, which was the backwards in time positrons and electrons and all that stuff with the diagrams. But how he derived his equation, they were like, "Yo, Dirac, how'd you derive that bad boy?" And he was like, "What's that? All I can hear you is that it gives the correct answer, and that's all you should be concerned with." And so that was a huge disaster for them at the thing. Everyone was disappointed, but there was nothing else to go with. So far, to recap, we have 2 lads putting together their calculations. One has no physical mechanism, a ton of math that no one can understand except for the person that wrote it. And we have Feynman, who has diagrams that no one can understand, where things go backwards in time, and it's actually physically repulsive to the people that heard it. They were really upset when they heard such obscenities. And
everyone understands that math nobody can understand is not only useless but meaningless, right? Like, it's not something to go just in case anyone was like, "Oh, I guess he's the smartest person in the world, being the only one able to understand the gibberish that he wrote." And it's like, no, it means that it's literally worthless. It has no value, right?
No,
absolutely
really
no value.
That's an amazing construct that you can come out with limitless numbers of different types of interactions that could be taking place, except that you can't measure them or detect them.
It is very interesting. So let's see here. I think
It's
we covered
Schrodinger 2.0.
You can let's see here. We got. So Feynman's trying to explain it. The boys aren't having it, but they didn't really have anything to go with. So so we'll just continue to read here. He says, let's see, make sure I'm back on track. The formula, where does it come? Yeah, so he's going over, where did the formula come from? And so I already went over that bit, but he has no explanation for how he derived it. He just has the equation. He just shows up. Do you guys remember taking the proficiency test in elementary school and whatnot, in high school and all that? On the math section, there was 2 problems where you had to show your work. You guys remember that? They got us with 2 every year.
Gosh,
and it was worth like 60% of your grade because you could calculate all the rest. They didn't care about that. They just wanted to know if you could do long division by hand, right? So show your work. Now Feynman does the most significant calculations in the history of quantum field theory. And they're like, show your work, Feynman. He's like, nah, G, just use the formula. I can't do it. I can't show you how I derived it. All I can tell you were stories about particles interacting. So to complete this mess, to complete this trinity, right? We need to bring in space-time because we haven't heard anything from old Einstein in a while. So there's one more thing that has to be imported into this quantum electrodynamic theory to really encapsulate the fact that this is definitely not an ether, and this is a discrete quantized energy packet interaction. So we have Tominaga comes in, and he points out that the equations that they're using are not relativistic because the way that they imply with quantum tunneling and instantaneous action at distance. And what's the other one? Did I mention entanglement, superposition, all that? Right? They use the same timeline for the interaction. So you can't do a Lorentz transform on that. You need a time and you need proper time. So you need proper time, and then you need a deviation from proper time. So this doesn't work for that. So so your boy Toganama goes to work on that, and he points out a second equation here that doesn't work out for them either, because you can tell that time plays a distinguishably different role than the other dimensional axes of the equation for the wave equation there. So he uses some renormalization techniques, does the old one over, but mentions here that even though he renormalized everything and made it give the appearance that it's cool, it still diverges, or it suffers from the same issue and diverges to infinities and has no physical meaningfulness. And hopefully somebody will come along and be a hero. And if Stone has that song, "We Need a Hero," like I don't know who wrote that, but we need a hero to come through and save us, dude. We need someone. And it's going to be Dyson Freeman who comes up with the Dyson series here. So here's a little sneak peek of the old Dicey series. So he's got G1 plus C sub 1 alpha over pi. And then it just keeps going on. You just add a little square there, and it just keeps going on for as many Feynman diagrams as you need to solve. You just add another, you just keep squaring it up. And that's called a Dyson series. So this is called the Heisenberg S matrix. And then he transforms that into what he calls the Dyson series. So what we're looking at here is this continuation series of just going up. It'll be, the next one will be 4, then 5, 6, 7, right? So with that, what he's calling that is the Dyson series. And the second coefficient of that is the Schwinger factor, right? So that guy Schwinger that used some numerology to come up with how he solved for alpha. They're using that as their coefficient, as their baseline to renormalize these and solve everything and bring it into physical meaningfulness to the theory, right?
So this was a grand.
So shout out to your
So
boy
this was
Dyson.
a grand program.
So I got an interview with him here, but we're not going to watch the whole thing. We can just skip to the end, but I'll just kind of narrate in my best English accent. No disrespect to your boy here.
Oh no! I mean, great. It'll be fun.
It was a jolly good time. It was a jolly good time, and we did a lot of interesting mathematics. Unfortunately, I came to the realization that there was an irrefutable argument that I made that nobody could refute, and it completely undermined the renormalization techniques that were used. Take it away, Dyson.
Published in a one-page note, and so that is a simple physical argument. Perturbation series divergent anyway, and no matter what you do, whether you separate high and low frequencies or not, the perturbation series in quantum electrodynamics simply diverges. And the argument to show that is a simple physical argument, which is published in a one-page note in the Physical Review Letters. So that was the end of the story. And that particular...
And then after that, I went back to jolly old England. Yeah. Yep.
Well, this was a grand...
Yes, sir. So we'll go over his argument here in a minute. It'll be towards it's a couple more slides down. But yeah, this went unrefuted, and he retired from QED after that. So that guy... This is a
grand program.
Sorry, this is the guy that merged Schwinger, Feynman diagrams, and Toganama's math for relativity. All those to make them, physically meaningless and covariant with established lore that there's no ether. This is the guy that brought it into that pioneered those renormalization techniques. Okay.
Your hero song has now been served in the live chat. Ding!
Thank you, sir. Oh, here we go. I'm going to play it real quick for your boy. Let's see.
So this was a grand program.
Your boy Chad Kroger, dude. Shout out to your boy. I did not expect that. All right. So let's see here. Okay, so I already went over this earlier, but to just recap here, Relativity theory is hindering everything, and it sucks. And this guy's had enough of it. Wants to start his own theory. All right. So Dyson. So we're going to go over Dyson talking about going through his process, right? Because this is one of the fathers of quantum electrodynamics as well. So he goes and talks to the Pope of physics. If you guys didn't know, every couple of years, the cardinals of physics get together and they vote on who's going to be I don't know. This is just this guy as a. Yep. Shout out to your boy. So he's the Pope of physics, Enrico Fermi. So Dyson goes to your boy Fermi in 1953. Fermi welcomed him politely. Now, this is alleged. Like, I don't know how polite it was, but this is from his account. So Fermi welcomed him politely, but he quickly put aside the graphs that Dyson was showing him, indicating agreement between theory and experiment. His verdict, Dyson remembered, was... Oh, yeah, so this is Dyson saying this. My bad. I was trying to set up your boy Pope. Let's see here. So there are two ways of doing the calculations in theoretical physics. One way, and this is the way that I prefer, is to have a clear physical picture of the process you are calculating. The other way is to have a precise, self-consistent mathematical formalism. You have neither. The stunned Dyson tried to counter by emphasizing agreement between experiment and calculation, and Fermi asked him how many free parameters had he used to make the fit. And Dyson says 4, and Fermi remarks back, I have an old friend named Johnny Newman who used to say, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. So with that, Dyson promptly retired from quantum electrodynamics and realized that what he had done was a bastardization of mathematics and applied to reality. And he felt really ashamed of that and went on to try. I don't know if that's true, but if that part's true, but anyway. He did go on to retire from quantum electrodynamics after that. So, and he says that he's thankful that he saved him and his students from being stuck in a blind alley, so he doesn't have to teach that nonsense anymore. So here, I super regret putting this format in the slide because it makes it hard to read. But basically, this is Feynman writing to the Pope of physics, right? So he's writing to Fermi, and he's saying, "Hey, man, heads up. There's a new accurate measurement with a muon. With the experimental first order values, the Feynman diagrams don't line up. So if anyone's trying to tell you that you can use a Feynman diagram to rectify this, don't believe them." Nah. So that was cool. Thanks for the heads up, Feynman. And so we go on to talk about the Feynman diagrams and those being the backbone for quantum electrodynamics and the electron weak theory and all of that. So the physical meaningfulness of what we just learned about with Dyson realizing that the reform, I haven't gone over why yet, but we'll look at that in a second here. So the complete abandonment of it based off of the mathematical techniques used to rein these equations in, the renormalization, it undermines all of these, right? Because when they get into quantum chromodynamics, where they talk about the pressure mediation or how the pressure mediation is dictated on the subatomic level, that's all contingent on these diagrams and solving these and the renormalization of these infinities that don't actually have meaningfulness. So let's see. We have Hans Bethe coming in again. So remember him from the first Lamb shift prediction where he used that K series, which diverged to infinity. So he comes out again with a new factor that he can with a new way to calculate that, and he's super excited about that. So he realized he just had to make some relativity corrections. He forgot to account for relativity the first time, and the second time when he remembered, he didn't have to use the divergent series. So he gets a smaller value out of that, and then it's more in alignment with the new experimental values, and everything's in alignment again. So what you'll see is that there's a series of, oh, dude, we got this experimental value that deviates. And then some guy comes along. He's the hero. He calculates everything. It's based off of all the coefficients to solve for this experimental value. And then what'll happen is a couple years later, someone will come along and, oops, that experimental value was actually wrong. This is the new value. And someone will come through and be like, oh, guess what, dog? If we renormalize everything again, we can, blah, blah, we can keep it going. So they just keep doing this over and over and over again. And by the 48th time, this happens 12 times, by the way. This is just going to be like a quick excerpt on the history of that. I'm not going to get into the each and every individual case of it, but this is just starting to build the pattern of what's going on with the predictions and the math and reality, right? They get a new value, they come up with new math. They get a new value, they come up with new math. They have free parameters which they can introduce to, rein the equations in and solve everything. They have no physical meaning. When we get to Guy's argument here, you'll understand why. So this is Gardner and Purcell, 1949. They come up with a new, let's see. Yeah, they found out that the Schwinger value was, no longer accurate, right? So this is the falsification of the previous mathematics used. They have a new experimental value for the G factor. So that magnetic moment that they're measuring, it has a new number associated with it now. So everything previous calculated and hinged upon from the Feynman diagrams and Schwinger and Tominaga and all that goes out the window. But Feynman's like, hold on, dog. we can apply the Dyson series to it and save everything. So remember, Dyson abandoned everything, but Feynman's here to say, hey, we can Dyson this up and still use everything because we're just changing the constants, right? So we got this nice matrix series here that we can apply to rein in our equations that diverge to infinity and give the appearance of physical meaningless. And everyone was like, oh, Feynman, you're the man. Woo, Feynman, you did. Woo, Feynman. And he was nominated for the Nobel Prize. Him, Toganama, and Schwinger were all nominated and received the Nobel Prize, if I'm not mistaken, for that. And so, let's see. So, yep, just another case of experiment not matching the theoretical prediction and then, just being reined in. So then we have Karplus and Kroll who come in 1950, and they are the first people to complete the Dyson reformalization, and they say that they complete it independent of each other. And they present this, the solution, which gives a coefficient for the series of minus 2,973, which allows them to, renormalize and rein in everything and do higher order approximations for their calculations to make everything, give the appearance that, yeah, we're just interacting with this quantized field and this uncharged particle is getting charged as it's accelerating due to its orbital radius around the nucleus of a blah, 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 right? All of that. So they're all super excited. They got this new value. They got a new Lamb shift value, and find with the correctness of the renormalization techniques you applied from Dyson to solve this to solve the Feynman diagrams. Everyone's super stoked, and that's where Feynman got the Nobel Prize and all that. Him and the lads. So we're going to go over Dyson's divergence of the perturbation theory in quantum electrodynamics. So he didn't touch on it in the interview there, but what he proposes is that if the techniques that they're doing are physically meaningful, then they should apply on an inverse system where electrons attract instead of repel. So like at the beginning of the Feynman video, or where they were going over the Feynman diagrams, and he was talking about the electrons and they repel. So that's why, when you're interacting with something, that's why you could have inertia and all that stuff, right? So he's saying if you apply it on the inverse, everything should work out. And it was a complete disaster. Everything diverges. There's no way to solve anything, no matter what you do to it. And then it gets into another problem where it creates vacuum instability, where the vacuum polarization becomes untenable because everything is spontaneously happening in the same occupied space. And there's just, it was a complete disaster. So it never actually converges in a meaningful way. And if it did, when he's doing it on the inverse, he's saying that, that would be that would be reflected in the mathematics, and it's not. So right after that, he completely abandoned it. So, and then, so then he went and talked to the Pope, right? And the Pope was like, yeah, dog, I see what you did there. And he was like, oh yeah, I did do that. Hats off. And then they all shook hands and parted ways. So we have Franken and Lebes who come in with a new measured G factor. So there's another new value, right? So that magnetic moment, right? The strength of that magnetic field gets measured with more precision. So that changes all their equations, or does it, right? Oh, well, guess what? When this experiment comes out, it just so happens that somebody comes out and finds out that Karplus and Kroll did some mathematical mischief with their solving of their equations and hinged everything on a diagram that they didn't show the work for and how they solved. And that's what gave that's how they were able to match their calculations to an experimental value that wasn't even the actual value, right? Because this new value that came out completely undermined it. So, so that gets completely ruined. And a guy comes along named Peterman and finds out that the value that when he applies margins of errors to the calculations, right? He finds that the maximum value that they could have gotten was 0.7. And then if you recall, they got negative 2.9. Yeah. So like everything hinged on that, right? So there's a massive discrepancy with no justification. And how could they produce that? How could they both have independently produced the same DS? Is there a superposition? Nope. Turns out they just got together and decided that they should check their work at the end. And in their compare and contrast, they hammered out the differences in their equations so that they would give the same result. Oh, no way. They just lied? That's cool. That's cool. And they, what's significant about this lie is the equations that they do. They're like, so they put together this 14-page paper, and it's, it gets real heavy in the diagrams. And they're like, look, there's these 2 diagrams and we have to solve these. It all hinges on this. And then like 4 pages later, they're like, okay, none of that matters. Everything we did's obsolete. Doesn't matter. Well, what really matters is these diagrams. And then those diagrams don't matter. And then at the end, he gets to diagram 2C, which is obviously, if you look at the numbers here, you'll see the significant figure that determines that gives them the negative 2.937 is this value for 2C, right? So this is the significant number here, the significant Feynman diagram. And they're like, okay, here, we'll show you how we solved it in the next paper. And they never published how they solved it. So that's cool, man. And, and they just conspired to get, so the 2 guys that didn't solve the same diagram independently didn't solve it and got the same value. Dude. Quantum mechanics is just strange and weird. And if you don't understand it.
What'd you get? Oh, all right, hold on. Well, that's not what, that's what I got too. I think we solved it.
I think we got it. So to give a little truncated recap of the history here, we have Karplus and Kroll, wrong value, unpublished solutions. Peterman comes along, corrects their value, but it unpublishes his solutions for how he solves it. So we're gonna see a series of nobody solving these Feynman diagram, the 2C diagram, or even showing how they renormalized it, right? So then we got Sommerfeld comes along in 1958. He's correct, but he uses a different series to solve it called the green function, and it doesn't use Feynman diagrams. So in 1960, Schmiz and Eulalie come along. He gets the correct one, but doesn't show how he solves it. And it just keeps happening over and over again. And then back to Schwinger again, who comes in. He hasn't got enough of the quantum electrodynamics, still thirsty for it, comes in and solves it without a Feynman diagram. Very cool. So let's see here. Now we're going to get into the EPR paradox, right? Because a lot of this hinges on, like Dirac was saying in 1963, he was saying, hey, because we're dealing with situations where the velocities don't necessarily have to mean anything because of quantum entanglement, quantum tunneling, etc., we can use quantum entanglement to describe these. Well, Einstein actually went ahead and debunked quantum entanglement. Went ahead and pre-dunked that for us because it threatened his theory because it implies an absolute reference frame. So he went ahead and swooped that up. Him and the boys got together and showed that you can solve the math for one system before it gets entangled as time progresses. And through that isolation of the first system, when it gets quantum entangled, blah, 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 you can actually solve for the second system without measuring it or disturbing it in any way. And this is unrefuted by Dirac and Heisenberg. They both, this actually was one of the things that made Dirac, throw in the towel for quantum electrodynamics, but then Niels Bohr convinced them to come back. But this went unanswered. And then Heisenberg was like, I'm going to refute this. And then he realized he made a mistake in the math. So he never published his refutation. And then he just never said anything else about it. So this is like an untalked about subject in quantum mechanics. This is known as the EPR paradox. It completely undermines the Heisenberg uncertainty principle. So a lot of like the whole of the physical interpretation of all this quantum weirdness and all this, hinges on things like the Heisenberg uncertainty principle being true to provide wave superposition and all that. So we're going to watch a video summary of that. So yeah, now we're going to get in. I'm going to play substitute teacher again. And the outro to this is going to be some pertinent videos to giving some understanding on some major quantum mechanics experiments and whatnot. So we'll start off with, the full screen here. Put that. Hold on a second. And it's just not gonna work, right? Oh no. 1 second. Sorry about that. Having some technical difficulties. Almost got it sorted. All right. So here we're going to watch. I did the double slit experiment at home. This is from a QED professor, if I'm not mistaken. She has a PhD in QED. So she does the double slit experiment on her home and realizes that light was a wave the whole time. Now there's a certain prediction that's supposed to happen here when the light goes through the slit. It's supposed to, when you introduce the slit, it's supposed to cause a different diffraction pattern for the light, but they only see a diffraction pattern that corresponds to a wave. And
you can see the narrow beam of the.
And she's like, oh, I thought that this, I always thought that the wave was the abstract mathematics and the particle was the real part. But when she goes in to measure, let's see, where's that diagram at? The real important part of it. 1 second. All right, this right here. So this pattern right here, she realized that this was the waves diffracting in, where they intersect to create the observed fringe pattern that they're looking at, and that's what made her realize that quantum electrodynamics is wrong about the wave particle duality situation, right? So here we're going to watch an experiment by It's BS where he introduces an additional variable aside from the position of the slit. He's going to introduce heat as a factor because they say that the problem with quantum with quantum supercomputers is ambient heat, and they have to operate at 0 Kelvin. So keeping them cool to maintain the superposition for them to do their calculations is a big problem, blah, blah, blah. So what happens if you were to do a double slit experiment and introduce ambient heat? Could you collapse the wave pattern with the wave function and see the actual double slit pattern for the quantized particle chunks? Well, let's see what happens.
So then how do you explain photons making this interference pattern? It is because the photon
I'll just let him go through the whole thing.
The absolute best experimental evidence against the existence of photons. So here is the basic setup for this experiment. We have a red laser pointer and a diffraction slide. The red laser pointer is a 650 nanometer wavelength. The diffraction slide was purchased from Amazon and is made by 3B Scientific. And here's a close-up of the diffraction slide. So now we can see the wave interference pattern that is created when the coherent light source, or the laser, is shot through this diffraction slide or through the double slit. You have the highest intensity light near the middle, and then you can see the bands of destructive interference where there is no light. So these waves interfered with each other and canceled each other out. And then bands of constructive interference where the light waves add to themselves. So light being a wave through a medium, which causes an interference pattern, explains this experiment logically. It only gets weird when you add in Einstein's confusion around photon particles and the illogical concept of wave-particle duality for light. So let's go ahead and play along with the idea of the photon particle applied to this experiment. There are plenty of videos that already go into detail about the double-slit experiment, but this Dr. Quantum animation seems to be a very popular one. And you can see right here, if you are shooting the idea of photon particles through the double slit, you would end up with 2 dots or 2 bands, as shown here. But when you do the experiment in real life, you don't see the 2 bands of these photon projectile particles. So then how do you explain photons making this interference pattern? It is because the photons are in a quantum state superposition. And while in that state, a single photon can pass through both slits at the same exact time and interfere with itself. This allows us to see the photon particles in an interference pattern like this because it is in a quantum state superposition at this time. So if the photon's quantum state superposition were to decohere right now, then it would go back to the 2 blobs that we saw on the Dr. Quantum picture. As you can see, this is some of the quantum weirdness that people talk about. Sure, it's weird, but it's because it's wrong, not because this is how nature works. So from a particle perspective, you're looking at a fully cohered quantum state superposition of photons. What I'm going to do now is add more noise to this environment to try to decohere this quantum state superposition of photons. Now, why would I do this? This is why quantum computing is not working, is based upon noise in the environment. Quantum computers are not working because they are having trouble maintaining quantum state superposition. And their reasoning is because there is external noise in the environment that is decohering the superposition that they're trying to maintain inside these computers. So why am I able to maintain this quantum state superposition of photons? So someone that understands the story of quantum physics would probably think I'm an idiot for using a heat gun.
All right, cool. We'll leave it at that one, and we'll move on to quantum entanglement. So this is going to be a recap on the EPR paper and the quantum entanglement, right? That uncertainty principle.
This is the 4-page paper that describes the extremely overhyped idea of quantum entanglement. It was written in 1935 by authors Einstein, Podolsky, and Rosen, and is commonly referred to as the EPR paradox. The purpose of this EPR paper was to use the math of Schrödinger's wave equation and disprove Heisenberg's uncertainty principle. The uncertainty principle is one of the core foundational papers of quantum mechanics, and Heisenberg tries to convince you that the world is inherently indeterministic. In other words, it is impossible to accurately predict what is going on in the world of atoms. We will come back to Heisenberg's paper later.
You drop out.
Testing.
We can hear you.
Okay.
Nope, you're good. The video just buffered out.
Locked up.
Huh. 1 second.
Bad
This is
YouTube.
You guys hear it
The
now?
4-page paper
Yep.
that describes
Okay. Cool. I think we were a couple seconds in here. That looks about right.
In other words, it is impossible to accurately predict what is going on in the world of atoms. We will come back to Heisenberg's paper later, but now let's look at a visual representation of what the EPR paper is describing. Schrödinger's equation describes how wave systems move. For example, you can think of this as a wave on the surface of a lake. Now forget that idea because quantum mechanics hijacked Schrödinger's equation. They want you to think of this as a wave of math, or specifically a wave of probability. So now we take the idea of electron particles and force them into a wave equation. And these waves each have their own wave equation associated to them. Now we take this 2-particle system and continue to evolve it over time. At this point, the two particles begin to interact and create what is known as a quantum state superposition. So going back to the EPR paper, we have a two-particle system that came together and interacted in the quantum state superposition, and now we will move this system forward in time so there's no longer any interaction between the two parts. So let's evolve this forward in time, and now we have the two parts separated again. So that's the basic logic behind the setup for this bug. We started with two separate equations, and then when they interacted, and this is the key, we can then combine those two separate equations into a single equation. This is where the bug begins because we now have a single equation that represents two separate particles. So then after the interaction, the combined system can then be calculated. So this is the system after the interaction, and here is how you exploit the bug. You measure only one of the particles in this two-particle system. Now, because you've measured only one particle, but this entire system is represented by a single equation, that means that this particle must collapse into a determined state. So the measurement of that single particle caused the entire wave equation to collapse. Now remember that one of the two particles was never directly measured or directly disturbed, and this becomes very important when it comes to disproving the Heisenberg uncertainty principle. Then the EPR paper goes on and describes, using math, what we now would consider quantum entanglement. And they finish the section by relating it directly to the Heisenberg uncertainty principle. What this is saying is that you can take a measurement from the first system and then use that information to plug it into the entanglement math. Then that will tell you what the second system is doing, without in any way disturbing or measuring the second system. Okay, so at this point, who cares? The EPR paper says all of this stuff, but what does it really mean? This was a direct attack on quantum mechanics and what we now call the Copenhagen interpretation. Paul Dirac was one of the main contributors to the Copenhagen interpretation. He was a skilled mathematician, and 2 years prior to the EPR paper, he had won a Nobel Prize for his work in quantum mechanics. Let's look at how Dirac responded to the EPR paper with this Niels Bohr interview that occurred one day before he passed away. So the interviewer commented that this paradox provoked a great stir among physicists. Dirac said several times, "Now we have to start all over again because Einstein has proved that it does not work." He also mentions that Heisenberg tried to write something to refute Einstein, but he made an error and therefore had to give it up. And he says it again and calls Heisenberg's attempt nonsense. And remember that Heisenberg wrote the uncertainty principle paper that is being directly invalidated by the EPR paper. And again, the question was asked, did Dirac think he had to give up quantum mechanics? Then Bohr replied, yes, at that time, but they had to convince him otherwise. So the EPR paper meant serious business. You had two of the mathematicians that founded quantum mechanics, and neither one could refute the EPR paper. At this point, the popular science stories will generally send you down the path of the great Bohr and Einstein debates. But the EPR bug is telling us that there's a problem with the uncertainty principle. Another name that Heisenberg wanted to use for this paper was the principle of indeterminism. In this paper, Heisenberg is trying to convince us that the quantum world cannot be determined by this type of continuous line, and you have to look at it as discrete points. But why is this? Heisenberg justifies this by discussing the problems of using a light photon to measure an electron. So at the instant when you try to measure the exact position, the electron undergoes a discontinuous change in momentum. So the more precisely you determine the position, the less precisely the momentum is known. In other words, if you know the exact position, you cannot know the momentum, and that is the indeterminism. So back to the EPR paper, they are measuring the first particle, and that allows them to predict with certainty, using the entanglement math, the values of the second particle. So that's the killer. You know the values of the second particle without disturbing it. So EPR is a workaround for Heisenberg's requirement that you disturb the system when you measure it. Let's look closer at how Heisenberg came up with that idea. He is using a gamma ray microscope to determine the position with as much accuracy as you want. The idea is that the gamma ray photon smashes into the electron, and that is what causes a discontinuous momentum in the electron, or that's what disturbs the electron. The next sentence is the exact bug for this paper, saying that the change in momentum is greater with smaller wavelengths of light means that he is using the 1 second photon energy per wavelength flaw. He is using Einstein's photon flaw to justify the indeterminism, or the discontinuous changes in the path of the electron. So this is where he uses Einstein's idea of high energy photons and his own idea of indeterminism. He is trying to figure out the orbit or the path of an electron in a hydrogen atom. You shoot a single gamma ray photon at the electron and that ejects it completely out of the hydrogen atom. So the path of an electron has absolutely no meaning, and it cannot be determined. So you can see here that Heisenberg's uncertainty is based on the idea of Einstein's high-energy photon flaw. This summarizes the problem with Heisenberg's uncertainty principle paper. If you don't understand the issue with this equation and what I'm calling the Einstein photon flaw, then you can take a look at these two videos on my channel that will help describe the issue to you. This one is the short version, and this one is the longer and more detailed version.
Highly recommend. They're awesome videos. I think we're going to wrap up.
Let's watch after the press.
Yeah, you want to? I'm down.
Yeah.
All right, then we're gonna have Sabine. We're gonna Toby, put the daggers away, bro. We're gonna have Sabine Hoffenstetter come on for a special guest to talk about quantum eraser.
Nice.
A lot of you have asked me to do a video
For
about
those of you who don't know, Toby and Sabine had a beef, but they said that Toby's willing to put it aside so that she could come on and talk about quantum eraser. So thank you for that. Much appreciated.
Tear it up, Sabine.
Let's go.
the delayed choice quantum eraser, an experiment that supposedly rewrites the past. I haven't done that simply because there are already lots of videos about it. For example, Matt from PBS Spacetime, the always amazing Joe Scott, and recently also John Lincoln from Fermilab. And how many videos do you really need about the same thing if that thing isn't a kitten in a box? However, having watched all those gentlemen's videos about quantum erasing, I think they're all wrong. The quantum eraser isn't remotely as weird as you think, doesn't actually erase anything, and certainly doesn't rewrite the past. And that's what we'll talk about today. Let's start with a puzzle that has nothing to do with quantum mechanics. Peter's 46 years old and he's captain of a container ship. He ships goods between two places that are 100 kilometers apart. Let's call them A and B. He starts his round trip at A with the ship only half full. 3/4 of the way to B, he adds more containers to fill the ship, which slows him down by a factor of 2. On the return trip, his ship is empty. How old is the captain? If you don't know the answer, let's rewind this question to the beginning. Peter's 46 years old and he's captain of a container ship. Peter's 46 years old. The answer's right there. Everything I told you after that was completely unnecessary and just there to confuse you. The quantum eraser is a puzzle just like this. The quantum eraser is an experiment that combines two quantum effects, interference and entanglement. Interference of quantum particles can itself be tested by the double-slit experiment. For the double-slit experiment, you shoot a coherent beam of particles at a plate with two thin openings. That's the double-slit. On the screen behind it, you then observe several lines, usually 5 or 7, but not 2. This is an interference pattern created by overlapping waves. When a crest meets a trough, the waves cancel and that makes a dark spot on the screen. When crest meets crest, they add up and that makes a bright spot. The amazing thing about the double slit is that you get this pattern even if you let only one particle at a time pass through the slits. This means that even single particles act like waves. We therefore describe quantum particles with a wave function usually denoted psi. The interesting thing about the double slit experiment is that if you measure which slit the particles go through, the interference pattern disappears. Instead, the particles behave like particles again and you get two blobs, one from each of the slits. Well, actually you don't, though you've almost certainly seen that elsewhere. Just because you know which slit the wave function goes through doesn't mean it stops being a wave function. It's just no longer a wave function going through two slits. It's now a wave function going through only one slit, so you get a one-slit diffraction pattern. What's that? That's also an interference pattern, but a fuzzier one, and indeed looks mostly like a blob, but a very blurry blob. And if you add the blobs from the two individual slits, they'll overlap and still pretty much look like one blob, not as you see in many videos, two cleanly separated ones. You may think this is nitpicking, but it'll be relevant to understanding the quantum eraser, so keep this in mind. It's not so relevant for the double slit experiment, because regardless of whether you think it's one blob or two, the sum of the images from both separate slits is not the image you get from both slits together. The double slit experiment therefore shows that in quantum mechanics, the result of a measurement depends on what you measure. Yes, that's weird. The other ingredient that you need
Nah, unless the thing you measured was always the thing it was.
for the quantum eraser is entanglement. I've talked about entanglement several times previously, so let me just briefly remind you. Entangled particles share some information, but you don't know which particle has which share until you measure it. It could be, for example, that you know the particles have a total spin of 0, but you don't know the spin of each individual particle. Entangled particles are handy because they allow you to measure quantum effects over large distances, which makes them super extra weird. Okay, now to the quantum.
All right, well, she already spilled the beans. The detectors are split, and you can recombine them to get the full interference pattern that you would see normally, and the mythology surrounding it is just kind of dubious. If we want to watch the full extended version, she plays out some animations that show the like, oh, if you measure it, it goes back in time and all that. But she just kind of like reiterates how that's full DS. And then when you recombine them, you get the same thing. So we can wrap that up. All right. So we got that. Got quantum. All right. I think that was everything. So to recap here at the end, let's skip to the end here. Was my end slide. Conclusions. What can we conclude from this? Where are my notes? All right. Well, the biggest conclusion we can make is that the renormalization techniques that are applied to solve these Feynman diagrams and give physical meaning to their equations is not meaningful, right? It's pretty obvious. They were like the founder of it even wanted to go back to an ether theory, but they really couldn't because everyone was on the special relativity grind. And we all know the history of that and the relationship to an ether as a fluid medium that permeates through all of space. And assuming there's even a space to permeate through, but I digress. It all hinges on people not showing their work and just the mythology around making you feel like you can't understand it. So to give a quick recap here, they're saying there's a quantizable electromagnetic field and that there's uncharged particles that have a certain mass to them. And when they interact with the field because of their intrinsic spin and orbital velocity around the nucleus of the atom in which they're, making up the material structure of, that they have that acceleration causes a magnetic moment that follows the right-hand rule, and they can actually measure the intensity of that magnetic field, and the measurement of that gave a deviation from their classically predicted amount of the quantization of the field, and that's where they came in with quantum electrodynamics ad hoc to come up with stories about how they could explain that through a physical mechanism that no one's ever observed or understood. It's only through measurement in abstract mathematics that's quote unquote renormalized to give physical meaning. All right, I think that about covers it. Any questions, comments, or concerns, boys?
Virtual particles that can't be observed, but they must needs be there, and they must needs be particles, and they're intermediating the energy discrepancies.
Yep.
Post hoc.
Dude, the straight face in which people are like, so when I'm measuring this, right, it's actually going back in time, rewriting history, doing the space-time continuum, adjusting things in the fourth dimension that actually adjust to show me that it was in fact a particle the whole time.
What? Well, that's one possible Feynman diagram, yeah.
And so then be like, all possible permutations must be answered simultaneously for you to use. Oh my god.
So at the beginning of the video, guy was talking about, when I was playing that science click video, he was talking about how you need to solve a certain amount of Feynman diagrams per the complexity of the situation, right? But there's an issue with how many Feynman diagrams you solve. There's like a diminishing return, so to speak. So the more complex the diagrams, the more infinity divergences you have to deal with. So when they first started out with these series, right, how many Feynman diagrams do you think they started out with? Right, there was the initial 5, and then the next series was like 50, and then a couple hundred, and then by the end of it, where they're at 8th order corrections, right? So they've taken the Dyson series close 12,750.
Nice.
So no less than 12,500 or 12,750 Feynman diagrams and 8th order corrections of a divergent series that never converges to a finite point. Can you say that quantum mechanics is accurate?
I like how that one guy was like, oh, you know what? If we inverse this mathematically, it should be fine. If we just, it breaks the hell down. You know what?
Yeah.
I'm out, guys. I'm out. See you later.
Yeah, so basically the claims that they make that, it's the most high precision agreement between prediction and experiment ever observed. What they actually are doing is they're simply just measuring stuff.
Yep.
They're comparing it to what they predicted it to be, seeing how much it's off by, and reincorporating
And then
the error.
correcting
and then remeasuring it. Dude, it sounded like a prediction if I ever heard one.
Dude, you guys, okay, so that paper that I got like pretty much all this information from and like did a timeline of, a guy does a reading of it, the channel pattern of logic or something like that, or something. It was his name, pattern QED. Yeah, it's 22 minutes. He just reads through and adds like what's it called, pictures and stuff to it. It's an awesome read through if you guys want to chill and listen to it. It's basically all the instances where they covered it up and brought it back, or just like readjusted it, because he goes over all 12 of them.
Well, that's pretty kick-ass, Alan. And
thank you, sir. Cool. I'm gonna pull up his video now.
Are you ending the live stream?
Can you go to one slide before that Asian dude there?
Absolutely. Give me 1 second.
Tamananga, bro?
Yeah, Tamananga.
Shout out to your boy Tamanaga. All right. Yeah, he does an excellent video on this, so we'll watch that in a second. Well, it's 28 minutes, a little lengthy, but we'll watch it at. Oh, sorry. Yeah, you want to see Tamanaga? What's up?
I don't know if it's a slide before this, but it's before him. It's like one slide before he comes up.
Oh, this was a great.
Before him.
Yeah. Oh, right. Yeah. Forward. Go. Just go to Tamanaka, and then it's the last slide before Tamanaka. Okay, right there. Yeah, this was the slide that. Okay, so you're telling me that Dirac said this is my mathematical formula, and I'll show you that it produces all the results of QED. They're like, where does it come? Feynman. He said, where's the formula come from? And he said, it doesn't matter where it comes from. It works. It's the right formula. How do you know it's the right formula? Because it works. It gives the right results. How do you know it gives the right answers? It will become evident from what I do with it. I'll show you how the formula works, and I'll do one problem after another with its help. So he's like, don't add. That's crazy, bro.
Yeah, dude, it's nuts.
Where it comes from. Does it get the right answer or not? Sit down and shut up. Let the big boys do the math. Dude, that's pretty much what he said.
Yeah. So take a seat, son. This positron's going backwards in time. So yeah, and then he called it tricks, right? The tricks they use to solve it. And he's basically just talking about the renormalization techniques where he could ignore certain things, et cetera. Because keep in mind, for his presentation, I'm not sure how many Feynman diagrams he solved off the top of the dome, but yeah.
So this is where they said like it gives the right results. Well, what it means is we figured out how much we were off by. We incorporated free variables into the equation, and in order to make it work. And don't ask us where they came from. Just worry about the fact that it works now. And that's nuts.
Yeah, and then when they came up with coefficients to solve the divergences from this based off of other experimental measurements, that's where they just like reincorporated in, and because it like reifies the math, they're like, oh, virtual particle annihilation, duh. It's like
what's that thing we just say when we can't explain stuff? Virtual particles. Got it.
So is this like is this like a widely known thing in like the PhD level of academia?
Yes.
That if you go to try to actually find the derivations of this stuff that they don't exist?
they do now is they put them under supercomputers, and most people. I'm sorry, I was stepping away here. So what they do now is they have supercomputers solve them, and there's no source code available for them, so you'll never know what techniques or how they're applying it to get the solution. But let's see, there was one other part I wanted to say. Can't remember now. It's just evaporated.
I think I'm going to start a new band. I'm going to call it Virtual Fudge.
Oh yeah. When they fudged that, like it just, that's why none of them could produce how they derived it, right? Like they were literally, the whole point of that conference was for Schwinger and Feynman to come through and be like, yeah, dog, so this is how we derived it. Like nobody cared that it gave the right answer, because they could all do that.
Yeah,
they could all do.
Funny that they were like super secret high five. We're gonna become best friends. We got the super best plan. No one's gonna figure us out. Oh, the secret is we told each other beforehand. Oh, we just decided that it was negative 2,900 and whatever.
Yeah, like I mean, anybody can just plug in an extra variable to account for the error and balance the equation out by.
Look at the Schwami fucking grins, dude, on these people. Look at the guy on the left. Like, yeah, I know.
For 7 years, they harvested and absorbed all the virtue of solving these DS diagrams. And we finally solved them with the renormalization from Dyson, and we have the coefficient for the second series, and we can now continue the masterful calc. Get out of here, dog.
Look at that guy.
And this is your boy Dyson, who was like, yeah, if we invert that, it doesn't work at all. Peace, I'm out.
Yep. I can tell by his eyes that he's not crazy. He's like, I've seen a lot of crazy, and I need to get out of here.
Yeah. So essentially, all of quantum computers are literally just a farce.
They're never going to work.
It's a huge scam. They don't work as advertised. What they do is they basically generate large data sets of data, and then they use they just RNG pull out some of that data, and because they're they extract a certain string, and they're like, oh my god, look, quantum computer, like it doesn't mean anything at all. No one cares. The whole industry is a complete failure.
No practicality to it.
So yeah, when they started doing it, there was all these investments came in, and there was a couple businesses that started up that were, we're going to be the quantum computer lads. And I remember watching YouTube videos on it, and they were like, yeah, we got to keep these bad boys liquid cool because 0 Kelvin, otherwise the blah, 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 right? I didn't really understand what they were talking about.
The qubit would flip.
Dude, HBS pulled that out. He's like, listen, all the noise, and it's like, oh, look, it's exactly the same, turns out.
So it's literally just bullshit.
Yeah, dude.
Keep the qubit in a superposition. It's all bullshit.
Yeah.
Wow.
Yeah, literally full DS, and it's just a ruse.
In high school, I learned about the double slit experiment. We thought it was crazy, but so you're
Yeah,
saying
dude,
it
it's like
turns out.
science is so mystics and mysterious. We don't really know anything. Like, what?
Were you saying? I mean, dude, is there an example? Because they say that when you actually observe the slits to see which one it goes through, then all of a sudden you just get two bands. I've never seen that. I've never seen the experiment done.
No one's ever seen the two bands, dog. Not a single person. That's why the whole thing is retarded.
Kind of like parallel, right? But no one's ever seen it.
Just no one has the fortitude to be like, hey, we're not seeing that. Right? And then they got so carried away with it that they split the detection and they split the detectors, and they show you one half of the detection of the interference pattern, and they're like, oh my god, there it is. There's that thing you were looking for. Like, oh my god, how did it happen? Well, what happened was your consciousness and like desire to measure it changed reality. Oh, okay.
Let's hit him with the Hermetic principles, the Hermetic philosophy, real quick.
Literally, insane. And shout out to
all truths are but half truths. All paradoxes may be reconciled. There you go. Have some Hermetic philosophy mixed in with that quantum. Boom.
What's up?
You're telling me they put a detector over each slit, and instead of just giving the fully recombinant like pattern on the wall back there, they just separated it into the detectors per each slit and said, here's one detector slit, let's look at that one only. Here's another one, let's look at that one only, and separated it apart so it looked like blobs instead of like instead of the actual like destructive interference.
Yes, sir.
Oh, you mean if I take away the second slit so that it can't interfere with the first, that I don't get destructive interference bands?
Well, it gives it an interference band, but because it's only half of it, because it's only showing half of the split beam, then it looks like the blob, right? But when you recombine the image from both detectors, it's the same interference band it always is.
Oh my gosh.
Yeah, they just straight rused everyone, dog. Like literal ruse. Not even it's just a ruse, dog.
Crazy.
It's literally just a ruse. Yeah.
He's like, yeah, no one has the fortitude to be like, by the way, we've all done this experiment. None of us is able to see two bands at any point ever. It's like, you're defunded. Shut up. Go away. Like,
Yeah. Yeah. Like,
man.
what do you mean there's a fluid medium that all motion's relative to and the Earth's stationary? Get out of here. It's like, Jesus, I didn't say any of that, but that's where it goes. Oh no.
Yeah.
So
my new physics course starts in 2 days. I can't wait to talk about electricity.
You're gonna get kicked out of your goddamn school, bro.
Yeah, absolutely.
No, the CIA is going to recruit him. They're going to be like, oh, this guy knows. Hey, have you ever seen Jack Ryan? Want to do that or whatever? All right,
we're all quite curious what's going to happen to Piezo.
I know.
With his
It's gonna be
question
awesome.
asking in school.
No, he's gonna be okay. You already
Quantum
cut out the microchip in his arm. He's good. We're good.
Yeah. Dude, he's off the grid now. All right, so this is 28 minutes, slightly longer than I expected, but if you guys are down to watch it, I am also down. So if there's no objections in the next 3 seconds, I'm already playing it.
Quantum mechanics is the idea of the absurd. Strange explanations like wave-particle duality, the uncertainty principle, and the collapse of the wave function. Things become even stranger when we consider the quantization of the electromagnetic field, including the polarization of the quantum vacuum, electrons and photons interacting with their own electromagnetic fields, particles traveling back in time, the emission and reception of virtual photons, or the continuous creation and destruction of electron-positron pairs in a quantum vacuum. Feynman summed it up as follows. The theory of quantum electrodynamics describes nature as absurd from the point of view of common sense, and it fully agrees with experiment. So I hope you can accept nature as she is, absurd. Electrodynamics is the branch of physics that deals with the effects arising from the interaction of electric charges and currents using an extension of the classical Newtonian model. It provides a description of electromagnetic phenomena whenever the relevant length scales and field strength are large enough that the quantum mechanical effects are negligible. For small distances and low field strength, such interactions are better described by quantum electrodynamics. In essence, it describes how light and matter interact. Quantum electrodynamics is considered the most accurate theory in the history of science. The precision is all based on a single experimental value, the anomalous magnetic moment of the electron called the G-factor. In this episode, I want to examine a paper by Oliver Conter, who examines the very suspicious coincidences, errors, mathematical inconsistencies, and renormalization of infinities which have been swept under the rug. Before we dive into the detail, it is important to understand a little bit about the history that led up to this. The Manhattan Project was a code name for the American-led effort to develop a functioning atomic weapon during the Second World War. It had been initiated in response to fears that the German scientists, led by none other than Heisenberg, had been working on a weapon using nuclear technology. It involved some of the leading scientific minds as well as the US military. The dropping of the atomic bombs on Hiroshima and Nagasaki, followed by the immediate surrender of Japan, gave the scientists of the Manhattan Project an elevated status. No longer were they harmless intellectuals. They were the powerful holders of the atomic bomb secrets. They were militarized and their knowledge became a state secret. The US government created the Atomic Energy Commission and appointed Oppenheimer as its chief advisor. Former members of the Manhattan Project took control of universities and research centers. They were allowed to invest in expensive experimental resources like supercomputers, particle accelerators, and atomic explosion tests through generous grants provided by the government. The credibility of former members of the Manhattan Project was almost unlimited. Their hypotheses were automatically accepted with no one dared to refute the theories. Worse, their calculations and experimental data were subject to military secrecy. So expensive was their equipment that it made it almost impossible for the international scientific community to perform the
She cannot take it, Captain.
Oh, I think it's Discord. I got the little yellow exclamation point in Discord. The stream you're viewing currently.
No, my connection's fine.
Yeah, it's all Discord's it. I think everything else is fine for me. If
Okay,
it,
good.
yeah,
Just
I'm gonna play
buffer
it for a
for a
second.
second.
If it's full DS, let me know.
Yeah, the stream you're currently viewing has reduced video or audio quality, maybe due to network conditions.
You know what? Let me put this on Let me put it on 720p because it doesn't really need to be 1080. All right, here we go.
Consequently, calculations of the experiment could not be reproduced independently. Those that accepted the hypotheses awarded a good job at research centers and universities.
Yeah.
And criticized the work were rejected and ostracized.
Full chop chop.
Yeah, full chop chop.
Son of a gun.
You should stop streaming and then restart.
All right, word.
I guess Discord needs another boost. Hey, boys.
Dude, it needs a booster. Oh yeah, it's lagging
Well
hard.
played.
I can hear it. All right, quantum electrodynamics. Start that again. All right, boys. Let me know if it's good.
Let's jump back just a little bit.
Good.
In 1928, Dirac published the first of his papers on the quantum theory of
Solid?
It's good.
Hello?
All good.
Okay.
the electron. In it, he had constructed a wave equation for the electron. It contained an outrageous leap of imagination. It entailed the explanation of spin as a consequence of the union of quantum mechanics and relativity. Prior to this, it was known that the electron had a spin. This was a fundamental property of the electron. In Dirac's equation, spin emerged as an inevitable property of an electron that was both a quantum particle and a relativistic one. Dirac's equation also revealed that there was a counterpart to the electron, the anti-electron, or positron. Based on the success of Dirac's equation, quantum mechanic theorists attempted to quantify the electromagnetic field by creating the quantum field theory. All attempts at this seemed to fail, as calculations under this theory resulted in an infinite number. Their solution to this problem was to simply ignore these infinities. Dirac was horrified by this, saying, "I must say that I am very dissatisfied with the situation because this so-called good theory does involve neglecting infinities which appear in its equations, ignoring them in an arbitrary way. This is just no sensible mathematics. Sensible mathematics involves disregarding a quantity when it is small, not neglecting it just because it is infinitely great and you do not want it." The technique of ignoring infinities is called renormalization. Even Feynman recognized that it is not a mathematically legitimate technique, stating, "The shell game that we play is technically called renormalization, but no matter how clever the word, it is still what I call a dippy process. Having to resort to such hocus pocus has prevented us from proving that the theory of quantum electrodynamics is mathematically self-consistent. It's surprising that the theory still hasn't been proven self-consistent one way or the other by now. I suspect that renormalization is not mathematically legitimate." In June of 1947, the first International Physics Conference after World War II was held at Shelter Island. It brought together 24 physicists from the Manhattan Project. The participants were received as celebrities, and it made a significant impact in the press. Two important experimental measures were presented. In the first, Lamb presented an experiment that showed the 2s½ and the 2p½ energy levels of the hydrogen atom were not identical. Instead, they differed by about 1,000 MHz. The other experiment showed a 0.1% anomaly in the hyperfine structure of hydrogen. Later, Bright would interpret this anomaly as the anomalous magnetic moment of the electron, called the G-factor. The problem was that both of these measurements contradicted the Dirac equation. So the meeting participants assumed Dirac's theory of the electron must be incomplete and proposed that these effects were due to the quantization of the electromagnetic field. They also assumed that the discrepancy could be calculated using quantum field theory, and that the infinities of that theory could be corrected using renormalization techniques. This is the origin of quantum electrodynamics. Sadly, Dirac was not at the conference and took a very dim view, saying renormalization is just a stopgap procedure. There must be some fundamental change in our ideas, probably a change just as fundamental as the passage from Bohr's orbit theory.
Can you hear the audio, Stone, or is it just not playing the video?
Nothing, not
far.
I
can
got
hear
the
everything.
floaty blocks.
Oh, I can hear it all.
Yeah, no issues here either.
I think I'm
can
going to
hear
learn
it.
that
It's
game.
fine.
Let me give it another shot. Back in a sec.
All right.
To quantum mechanics. When you get a number turning out to be infinite, which ought to be finite, you should admit that there is something wrong with your equations, and not hope that you can get a good theory just by doctoring up that number. A little while after the conference, Bethe published a paper outlining an equation for the Lamb shift. And here is the equation. What is important is that the value of k on the right-hand side diverges to infinity. So Bethe decided to apply renormalization by substituting the infinite values for the finite value of the electron's energy, so k equals mc². The problem is that there is no physical justification for making this change. The only reason to use it is that the final result do yield a value that was close to the experimental value. A few months after Bethe's paper, Schwinger attempted to calculate the G-factor for the electron. Here is his equation for G. Here, alpha is what is known as the fine structure constant. It is a fundamental physical constant. It effectively determines the size of the splitting of the fine structure of the hydrogen spectral lines. It was considered to be important under Dirac's linear relativistic wave equation, which gave the exact fine structure formula. Schwinger's value seems to be very close to the experimental value, which had previously been published. He never explained how he derived his equation, and stated that he would publish a paper outlining the details of his theory soon. Schwinger had assumed that the G factor should be directly related to the fine structure constant, which has an approximate value of 0.7%. Dividing this value by 6 or 2 pi provides an approximate value of 0.1%, which is the value that had been obtained experimentally. At this point, you might consider this a mere coincidence, but as you will see, this coincidence keeps happening, and coupled with the fact that he never published any document explaining his method, sets the stage for quite an unbelievable web of deceit. Schwinger's value had a significant impact on the scientific community due to its simplicity and accuracy. Everyone waited in anticipation of Schwinger's theory. None would ever be forthcoming. The following year, 1948, a second conference took place. It was attended by the same participants as the previous one, but this time Bohr, Dirac, and Fermi attended as well. The conference was focused on Schwinger's presentation. Hopes were high that he would finally present an explanation for how he had calculated the Schwinger factor. When Schwinger finally presented, it went on for 5 hours. He presented a series of complex and totally incomprehensible equations. Oppenheimer was not impressed, saying, "Others gave talks to show how to do the calculations, while Schwinger gave talks to show that only he could do it." The following day, Feynman would present his theory, and would be the first time to show his famous Feynman diagrams. Most attendees did not respond positively to them, but Feynman was convinced of the validity of his calculations simply because they produced the correct result. Bethe had the following to say after the conference. Schwinger and Feynman respectively presented their theories. Their theories seemed to be totally different. Schwinger's was closely connected to the known quantum electrodynamics, so Niels Bohr, who was in the audience, was immediately convinced this was correct. And then Feynman came along with his completely new ideas, which, among other things, involved positrons going backwards in time, and Niels Bohr was shocked. This couldn't possibly be true, and gave Feynman a very hard time. Feynman's recollection is very revealing. This meeting was very exciting because Schwinger was going to tell how he did things and I was to explain mine. We could talk back and forth without going into details, but nobody there understood either of us. I didn't have a mathematical scheme to talk about. Actually, I discovered one mathematical expression from which all my diagrams, rules, and formulas come out. The only way I knew that one of my formulas worked was when I got the right results from it. There were now 2 competing theories for quantum electrodynamics, and a third would enter the ring submitted by a Japanese physicist named Tomonaga. The hunt was now on to find a way to unify these theories. The person leading this charge was English physicist Freeman Dyson. Dyson proposed that the Heisenberg scattering matrix could be used to calculate the electron's G factor, transforming it into a series called the Dyson series. The Dyson series was an infinite series of powers of alphas, where the first coefficient was precisely the Schwinger factor, and where each coefficient could be calculated by solving a certain number of Feynman diagrams. By basing his theory on Feynman's diagrams, it provided the solution others had been waiting for. But not all were happy with this approach. Oppenheimer felt that it was entirely the wrong path. He did not believe that Schwinger and Feynman's ideas had much to do with reality. He felt that physics was in need of a radically new idea, and that the quantum electrodynamics of Schwinger and Feynman was just another misguided attempt to patch up old ideas with fancy mathematics. Dirac too felt it was not the correct approach, and stated the following. How then do they manage these incorrect equations? These equations lead to infinity when one tries to solve them. These infinities ought not to be there. They remove them artificially. Just because the results happen to be in agreement with observations does not prove that one's theory is correct. Fermi was also appalled by the theory. His comment was as follows. There are 2 ways of doing calculations in theoretical physics. One way, and this is the way I prefer, is to have a clear physical picture of the process you are calculating. The other way is to have a precise, self-consistent formalism. You have neither. Feynman's response to these critics is well known. Shut up and calculate. The following year, a third conference was held with the same participants. Feynman stole the show with his immense charisma. He presented Dyson's theory as the definitive formalization of the quantum electrodynamic theory. From that point on, Feynman's diagrams became a popular tool among American physicists, and Feynman took over as the leader of this new generation of scientists. Further research would result in the formulation of quantum chromodynamics, the electroweak theory, and the standard model of particle physics. But these all rely heavily on the use of Feynman diagrams. These are only valid when the coupling constant has a very low value. If alpha is greater than 1, the Dyson series diverges. In the case of fermions, the coupling constant is greater than 1. This means that it is not mathematically legitimate to use Feynman diagrams for the calculations. In 1951, Feynman himself warned of this problem and actually said, "Don't believe any calculations in meson theory that uses a Feynman diagram." In 1949, Gardner and Purcell obtained a new experimental result for the g-factor of 1.001146. This now meant that the Schwinger factor was no longer considered accurate. This was Feynman's opportunity to push Dyson's theory. A year later, Karplus and Kroll completed the complex calculations and published a value of -2.973 for the second coefficient in the Dyson series. For the second time, the new theoretical value was in good agreement with the new experimental value. Quantum electrodynamics had triumphed. Feynman's prestige dramatically increased. In 1952, Dyson published a paper titled Divergence of Perturbation Theory in Quantum Electrodynamics. This paper outlined that all the power series expansions currently in use in quantum electrodynamics are divergent after renormalization of mass and charge. Dyson, the creator of the theory that seemingly fixed the problems in quantum electrodynamics, was calling into question the nature of the physical concepts upon which the theory was built. This was a massive blow to Dyson and caused him to move back to England and abandon this line of research in favour of examining other areas in physics. Strangely, no one seemed to pay any attention to Dyson's paper, and quantum electrodynamics credibility was unscathed. In 1956, Franken and Liebes conducted experiments which provided a very different g-factor value, this time 1.001165. This time higher than the Schwinger factor. This meant that the second coefficient, which had been calculated by Kroll and Karplus, actually made the theoretical value worse. Based on the new experimental data, this second coefficient should be plus 0.7 instead of minus 2.973. The difference was huge and raised the question of why Kroll and Karplus's value had provided the exact expected experimental value when the value now turned out to be incorrect. It becomes evident that the quantum electrodynamic calculations had been engineered to match the experimental data. Karplus and Kroll confessed that they had not independently reached the same result, instead reaching a consensus result, and admitted that it was possible that there were errors in the calculations. Feynman would later claim that this was merely a mistake in arithmetic. And once the mistake was found, all was once more in agreement. 7 years after Kroll and Karplus first published their paper, Peterman detected another error in their calculation. When he then corrected this mistake, he obtained a result of minus 0.328, which was almost 10 times smaller than the original value. In 1953, a new type of experiment was proposed to calculate the magnetic moment of the electron directly from the precession of the free electron spin. In 1961, based on this method, Shupp, Pidd, and Crane carried out the experiment and obtained a new value of 1.0011609. This method should have provided a much more precise measurement, but the authors were very cautious and used a large margin of error. The estimated systematic standard error was 0.000004. If they had used this error, it would have meant Peterman's theoretical value was outside the margin of error, creating a new crisis in quantum electrodynamics. They conducted a series of runs for different electron energies. The weighted average of this is 0.0011627 plus or minus 0.000020. This falls outside of Peterman's theoretical value. So how did they come up with a single value? They felt they needed to recognize the trend of the points. So the way they were able to obtain the value that still aligned with Peterman's one is by taking this single value, adding the error from that to the averaged error to obtain a final value of 0.011609, plus or minus 0.000024. 2 years later, in 1960.
Oh yeah, you just adjust your margin of error to fit the old math. There you go.
1963, Wilkinson and Crane published an improved version of the experiment. This time, the value was 1.0011596622 plus or minus 0.00000027, nearly the same as Peterman's theoretical value. This experiment was conducted at the same university with the same team. This makes it very strange that all the measurements from the previous experiment were outside of the range of the new experimental value. It also fits perfectly with the theoretical value. The most disturbing aspect is that the value is not correct, as was demonstrated in later experiments. In 1965, Drell and Pagels published the first calculation of the third coefficient of the Dyson series. This required solving 72 Feynman diagrams. The result was 0.15 and resulted in a slight change to the value of the electron g-factor. Based on this, all doubts about quantum electrodynamics were cleared. Feynman, Schwinger, and Tominaga were awarded the Nobel Prize in Physics. In 1968, Rich re-evaluated the Wilkinson experiment and obtained a different result. Other researchers would find further errors in the experiment. 2 years later, Rich and Wesley repeated the experiment, fixing the detected ambiguities, and obtained a result higher than the previous one. That same year, Brodsky and Drell recalculated the third coefficient and obtained a different value, 3 times higher than the previous one. Conveniently, the new coefficient and the new experimental value were once more in agreement. Brodsky and Drell summarize the situation as follows. Quantum electrodynamics has never been more successful in its confrontation with experiment. However, and despite its phenomenal success, the fundamental problem of renormalization in local field theory and the nature of the exact solutions of quantum electrodynamics are still to be resolved. From this point onwards, all the mathematical calculations required to obtain the coefficients of the Dyson series would be performed by a computer. No source code for these calculations has ever been published, making it impossible to reproduce any calculations independently. In 1971, Levine and Wright recalculated the third coefficient, and once more, it was 3 times higher than the previous one. The same year, Wesley and Rich published their final results for the experiment, as the previous results had apparently only been preliminary. Their final results were slightly higher than the previous one. By another striking coincidence, this new coefficient and the new results once more seemed to match up. A few months later, Kinoshita and Kvitanovich published a new calculation for the third coefficient. They claimed it was 5 times more accurate than Levine and Wright's previous one. This time, it was slightly lower and made the agreement with the experimental value slightly worse. In 1977, Van Dyck and de Melt used a new technique to obtain a new experimental value. Once more, the experimental results did not match the theory. In order to resolve this, the theoretical physicists felt they needed to calculate the fourth coefficient. This involved solving 891 Feynman diagrams. 4 years later, Kinoshita and Lindquist published the first calculations of the fourth coefficient, with a value of minus 0.8. But then, in 1982, Levine published a new calculation of the third coefficient, and again, it was lower than the previous one. This once more brought the theoretical value in line with the experimental one. Van Dyck and de Melt published 2 more results in 1984 and then again in 1987, and once more brought the experimental value out of line with the theoretical one. In 1995, Kinoshita's team published a new value for the fourth coefficient, almost double their previous value at minus 1.557. The following year, Laporte and Remedi would publish a new value for the third coefficient at plus 1.181. These would once more bring the experimental results in line with the theoretical. The muon's G factor. A muon is almost identical to an electron, except that it seems to have a much greater mass. Quantum electrodynamics was used to calculate the anomalous magnetic moment of the muon. A muon is very unstable, making high-resolution measurements very difficult. CERN made the first measurement, and unfortunately, the theoretical value did not match the experimental one. In order to solve this problem, they decided to add in adjustment factors. These factors would be taken from the standard model of particle physics. The first coefficient would be derived from the interaction of the electron with a lepton, the second from the electroweak interaction, and the third from the interaction of the electron with hadrons. These factors, unsurprisingly, did bring the new theoretical value much closer in line with the experimental.
Oh, dude, you can just inject more mechanisms to
tune your predictions to match reality.
Wow, that's so cool that they were able to do that. Wow.
Good
Dude,
for
you know
them.
what's definitely not real? Ether. This is for real. This makes so much sense, dude.
They went through like 5 or 6 cycles of, okay, we found it, it matches experiment. Oh, we updated it doesn't match experiment. Okay, we redid it matches experiment. Okay, we updated it doesn't match. And like further and further, like back and forth, it matches, it doesn't, it matches.
And then at the end of those 10 times permutations, they're like, look how accurate the best, most accurate physics experiment in all of history is, down to not 0.1. We nailed it.
Oh, look, we measured it and it's outside our perimeters. Well, hold on, boys. We got to calculate for the weak effect, the strong effect, the boson field, the non-boson field, what the particle was like before it entered reality. And we got to, it's like, dude, what the, get out of here, dog. Get out of here. This is crazy, dude.
But we can't show you the source. No one can see the source code. Just trust that the computer is doing it right.
Just trust that the renormalization. Trust in renormalizations we trust. Haven't you ever seen the back of a quarter, my boy?
But what kind of diagrams are we going to use if we can't use Feynman diagrams? I don't know. I don't know what's going to happen. Oh my God.
Oh, maybe we can use a little greens function.
Oh.
Why is it in that voice?
I don't know.
Like it seems fitting, but it's I don't know. Anyway.
Soy V.
This change unfortunately made the theoretical electron
Soy
G
V
value worse,
council.
and this created yet another discrepancy. In 2006, Harvard improved the electron measurements even further. In 2007, Kinoshita's team detected an error in their previous calculations of the fourth coefficient.
Oh, no
They
way.
had found
were
an
wrong the whole
inconsistency in the old treatment of infrared subtraction terms in two diagrams. When they corrected for this, the new value came out as minus 1.914. With these changes, the new theoretical value was once more in good agreement with the new experimental value. In 2012, Kinoshita's team published the first fifth coefficient. This involved calculations based on 12,672 Feynman diagrams. They also published a slightly improved value for the fourth coefficient. 3 years later, they would publish an improved value for both. Then, in 2018, they once more detected an error in their previous calculations of the fifth coefficient. All the while these corrections were ongoing, the muon G-factor experimental results refused to come into line with theoretical predictions. These persist even today. According to Feynman, we have found nothing wrong with the theory of quantum electrodynamics. It is therefore the jewel of physics, our proudest possession. But maybe the sentiment is better portrayed by Dyson, who wrote in 2006, as one of the inventors of quantum electrodynamics, I remember that we thought of quantum electrodynamics in 1949 as a temporary and jerry-built structure, with mathematical inconsistencies and renormalized infinities swept under the rug. We did not expect it to last more than 10 years before some more solidly built theory would replace it. Now 57 years have gone by, and that ramshackle structure still stands. It is important to understand that all calculations performed in quantum electrodynamics always result in an infinite value. Renormalization techniques have to be used to convert this into a finite number. These techniques are not valid mathematically. Despite this, they are used to provide results that fit perfectly with experimental results. It should not come as a surprise that errors continue to appear in the calculations. Each Feynman diagram implies the resolution of multiple factors, and each of these diverges to infinity. So renormalization techniques are arbitrarily used to eliminate these. I hope you've enjoyed this insight into the deep and dark world of quantum electrodynamics. If you did enjoy it, I would appreciate a thumbs up, subscribe if you're not subscribed, and if you'd like to help support the channel, you can via Patreon, PayPal, or Super Thanks on YouTube.
What number can we plug into each of these coefficients in order to make this get as close to experimental value as we can make it? Like, well, the more terms that we incorporate, the more sensitive it is to change, and so we really have to run through like a bajillion permutations to get it as close as we can, and it's still never going to be exact, so we get it as close as we can. Oh, we figured out we can add another term and also incorporate this other stuff to get it even closer, but it still doesn't match. But we say it's close enough, and it's the closest agreement between experiment and prediction in the history of science. Okay.
Those muons are very elusive. Their magnetic moments are said to be anomalous.
But dude,
right?
they're actually dude, they're just literally it's crazy, dude. They're hand tuning coefficients in order to make it match what they observe.
Well, to quote the Pope of Physics, my boy Johnny Newman once said that if you have 4 free parameters, you can fit an elephant in there. And if you get a 5th free parameter, you can make its trunk wiggle. Old Johnny Newman was a pretty wise lad.
Yeah.
And I mean, they have what? Do they have 5 coefficients right now?
I mean, how many do you need, dog?
Well, as many as you need, as long as you keep getting not matching reality.
Each time you add a power or alpha series to the old Dyson or whatever, you have to get a new coefficient.
Yeah,
so you can have an infinite amount of correctness. How cool is that? And then, if you're ever experimentally wrong, you can renormalize the whole thing and always be correct. How cool is that, dog? To never be wrong.
So cool.
You know what's funny is like there's this back and forth where they're like, dude, we're going to replace quantum electrodynamics. We're going to merge it with grad. Like, you guys ain't going to do shit. You have the only viable way to pretend that there's not an ether, and it's logically retarded, and there's no other way to go from here. This is as retarded and as complicated as that they can make it, and there's no fixing this without acknowledging an ether.
What's that paper from the Oliver guy? Oliver, whatever. There's something wrong with the state of QED or whatever.
Yeah,
he says how the basically the physics around it got militarized and is like got like scooped up and classified, and we just get fed the retarded version.
Yup. Sounds very similar to what you said.
You had it. It was linked in your paper.
I know. I'm pulling it up.
Or
I'm pulling
not,
up
or
the
your
exact paper for you.
Your Prezi, I mean, sorry.
I was kidding. That's exactly what you said. But here's the paper.
It's like, let me change my window.
There you go.
Oliver Consa.
Shout out to your boy.
Whoa, your mic's echoing now.
How does it sound now?
Whoa,
Oh my
echoing.
god.
Stop talking. It's terrible. Everything's terrible.
Are you sharing your...
Did you like release your mic and duplicate your mic input in OBS by any chance? Because that's exactly what it sounds like.
So what happened was...
Oh, it's because we're looking at your stream and it's coming to the stream volume.
Yeah, all of a sudden it started coming to the
Stop
stream.
watching that. Yeah.
Yeah, so it should be good now.
Excellent. Whew.
Fixed.
All right, cool.
Thought you were a
GG.
Morgan Freeman god.
I thought you were a real cyborg for a second.
Nice. Very cool. All right, so if there's no further questions, comments, or concerns, I think we can wrap this episode up.
Great. Well, thank you everyone for tuning in for Roundtable number 34, Æther Roundtable 34. Thanks, Alan, for such a fantastic presentation. And thanks, Feynman, for not adhering to any sort of explanatory science or anything, just pure calculations that he couldn't even, just pull them out of anywhere, go back in time. Nice job, buddy.
Shut up and calculate, Toby.
So
My salary depends on it.
So yeah, shout out to all the physicists that got to keep their jobs thanks to Feynman, and continue to keep their jobs thanks to Feynman. So yeah. In any case, thanks seriously everyone for listening in and for being here with us. And on Thursday night, join us again for another X Twitter live space where we'll talk, kind of an open discussion. We'll probably talk a little bit about this quantum electrodynamics stuff, and then we'll just do a bit of an open discussion and kind of a open mic type of thing Thursday night. So join us for that on X Twitter Spaces. And then, as always, join us next week for Monday night reading night, Tuesday night. Actually, Tuesday night, we have a very exciting, very special guest coming.
That's right.
Or we'll just go ahead and say Dr. Robert Bennett will be showing up to give, we're going to go ahead and call it Æther Roundtable number 35. And he's going to give his presentation, his first part of 2, regarding the Hildegard model. So we're really looking forward to that. If you're not familiar with Robert Bennett's work, I highly recommend you go check out on Wits It Gets It's channel. There are a couple of In the Fields with Robert Bennett. Go listen to those. Those are absolutely fantastic because Bennett gives his full presentation from start to finish across both of those. And then if you want even more of that, come listen on either Space Audits or on either Cosmology and go find the times that Bennett has come and joined us for Æther Roundtables, wherein we watched some Aussies and also just a few other random videos and a few other random discussions wherein Bennett came and talked with us. And actually, he came in when we were watching his content at one point. So in any case, we're really looking forward to the Hildegard model presentation. So join us for that next Tuesday. And take care, everybody.
Yeah, before we exit out, I provided links to a PDF of the Hildegard Æther model that he's gonna be going over. Everything that he's going to be covering is after page 100. So if you guys want to grab the PDF when you get a chance, take a look at it. Everything after page 100 will be the relevant portions. So if you have any questions or comments that you want to ask for Bennett, send them to allanspaceaudits@gmail.com. And the title, put Bennett Prez or something Prez, and I'll know what it's for, and we'll get to those questions during the presentation.
Is that on Æther? Is that on ethercosmology.com?
Yep. Yeah, I put a link in the live chat on Discord, and I put one in the stream chat.
Excellent. So yeah, just go to ethercosmology.com and you'll find it posted by Alan within the last couple days here, or just grab it out of the live chat there. So yeah, thanks everyone for listening in, and take good care of yourselves.